like to present the work of our team. The top of my presentation is physics-inspired multimodal feature fusion cascaded networks for data-driven magnetic loss modeling. As you can see, our presentation will be divided into 4 parts. To start with, I will provide a bit of background information about the work we have done. Through researchers, we found some limitations of the existing neural network-based methods. On the one hand, the data model of the input in the current models are usually single, such as scalar to scalar or sequence to scalar. And on the other hand, due to the voltage is usually imposed in power converse, so flux density is more relevant and accessible than magnetic field. Thus, HT is restricted to not be used as input in the practical application. And so our work want to provide the physics-inspired multimodal feature fusion cascaded network for modeling. The proposed methodology consists of 2 cascaded submodules. Firstly, a physical-inspired network model, submodule A, based on macro-magnetism and red LG equation is proposed. Submodule A aims to provide new sequence information HLG for the next cascaded submodule B. This addresses the limitation where flux magnetic field waveforms are able to take part in the actual prediction process. And with embedded macro-magnetic parameters in the granted learning processes, the training submodule A can be regarded as the inverse model of LLG equation. And furthermore, to solve a series challenges in multimodal information learning, we provide a multimodal future fusion-based network, i.e. submodule B. The model B combines CNN and FCN to learn deeply from hybrid sequence scalar data. Is specifically a parallel CNN branches for sequence feature mappings, followed by consolidating these mappings with other scalar data into FCN for global learning. And through this, the models have good generalization and robustness. And the experiments results of submodule A is showing. With iterations of epochs, the parameter and characteristics, the inverse model test is performed by taking a flux density to replace a flux density LG characterized by LG equation as input to the world submodule A. Figure 3 shows the comparison of predicted HLG with the true magnetic field after input data changes. The results show that they tend to maintain similar sharp features after several training epochs. Even some samples perform poorly. They still maintain the same key characteristics as the true magnetic field waveform, which is helpful to the following color loss prediction. Having submodule A can effectively provide the design inspirations of enriching the hybrid multimodal features. They are contributing to improve the generalization and robustness of the color loss modeling. There is the submodule A is the out of submodule is to take as an input of the submodule B, and after the transfer process of submodule B, it offers the Promost model B also maintains good performance in materials. With when big data is all small sets. It proves that the Promos has a strong generous ability and can adapt to the properties of different materials. However, there is still some unsolved difficulties. First is the number of parameters in the model is relatively large. And the other is too few training dataset may affect model performance. So that's why our model perform not very well in the finally testing. That's all my work have done.
Thank you, Yukon. Very, very interesting talk. I guess my question will be, well, what's your thoughts in how do you reduce the size of your model? What's the thinking behind it?
After the we learn from other team, I think I learn a lot. Maybe I think FFD is a master more good way, and in addition, I think LSTM and could bring memory in our model to reduce the model size of two.
So you use CNN, right?
Yes.
So did you try like normalization and downsampling? Are you processing the entire 1000 time sequences? 1024.
I use a scroll to the data into small size after small size.
So you are downsampling. You're downsampling, but you're processing it with CNN.
Yes, yes.
Okay, understand. Okay, great. Any other question?
Yeah, I have a question, Wilhelm Kirchgesser. For how many epochs have you trained the models?
How many epochs?
For most of Model A, just several epochs because I just want to get a model which can provide the features but for some Model B, we train it after within about 500 epochs. 500 epochs.
And for Model A, it was just 10 or so, or more?
Because due to the execution, we train it in 10 epochs or 100 epochs. We find 100 epochs perform same as 10 epochs. So we use it to get a similar magnetic field feature within several epochs to save time, to save the total training time.
Okay.
Yeah. So
maybe you can improve the accuracy easily by training longer or more epochs.
Oh, okay.
Yep.
Thank you for the advice.
Yeah, we already after the town hall meetings, these 3 town hall meetings, we already learned quite interesting difference between CNN and memory-based networks, LSTM and transformers. CNN, you can get very compact size and may work well for periodic signal, and maybe that's the choice. And maybe we should try it too. Like I'm interested in understanding the difference between CNN and LSTM. But for transient, if we ultimately have some kind of transient data and try to model the physics, then physics has causality. So maybe a memory-based method will be more promising, but then the price we have to pay is we need larger model and more data to train. So yeah, this is very, very interesting. Now, if we add transient dynamics into it, the data size we have to double or even triple or or another order of magnitude larger for the data for training. So yeah, anyway, so these are very, very interesting exploration. Any other question or comments?
Just a quick question. So I noticed in your experimental result, the predicted the waveform of the H, especially for those trapezoidal waveforms, it looked like the predicted result is quite noisy. There's some fluctuation there. Have you looked into that? Like why this happened? Did it come from the LLG equation or from your neural network is doing some kind of like a overfitting?
Yeah. I think LG is have to reduce overfitting and in the training of some model B, we also introduce regularization and L2 regulation to improve the overfitting, and the Hue loss and also was inviting to improve it.
Okay. All right. Let's move on. And